Hello, here we will talk about solutions of linear systems, starting with homogeneous. And introduce the basics of vector arithmetics. So let's imagine a homogeneous system of linear equations. X's will be unknowns, all the rest will be numbers, like a coefficients for the left side of the system. So yeah, I'm imagining a homogeneous system, the right hand side are all zeros. And we'll have m equations in the system. The first observation, which we already used before, is that the system is always solvable, always has a solution written in this vector form, which consists of just zeros. That means that if we replace our unknowns by zero, all equations will be true. And that is because the right hand sides are all zeros. But we can say even more. Assuming that we know some solutions, we could produce other solutions. Let's imagine we have two solutions. Again, I'm writing them as vectors of the components of these values for x. So this is a collection of some numbers which solve all the equations, and then imagining having another such collection, which is a solution. Then this is a sign for implication. Then this will imply that another collection, which consists of sums of these values for unknowns, will be a solution of the system. Let's check. We have a bunch of homogeneous linear equations. It's enough to just check for one. And I will, for that, I will drop the first index, which labels the equation from all the coefficients. So I have the condition that the first collection of numbers solves my equation. And at the same time, the second collection is also a solution, so I have these two equations. And now I need to check that the collection which consists of pairwise sums is also a solution. So I need just to write what the equation, oh, it's x1 prime, this equation, what the sum is. And what I can do is to distribute the products through the little sums and then recombine the things with x's first, and then follow with sum of products of primed numbers. Each of them is a solution, each of these collections is a solution, and that means, as we have it written here, that each of these two sums is equal to 0, which gives a total 0. So that means that the collection, the vector with components being sums, is a solution as well. This operation on vectors, taking 2 and producing 1 by computing the pairwise sums, is called the vector addition. So what we have is a sum of two vectors. I'm writing them vertically because it's good to see how things are aligned. So that is the sum of vectors. In this case, sum of solutions. We checked it for one equation, but now we can imagine that this equation is either the first or the second or anything till the last. And for each of them, we'll have the same thing happens, that the two solutions summed up will be solving each of those equations. So we have it proved. The second statement we can make about solutions of a homogeneous system is that if we have a solution, then multiplying it by a number in every component will also be a solution. The checking is done analogously, so we know that the solution makes this equation true, and then we have to check it for the collection where all the components are scaled by the same number. So we just write what happens when we substitute it into the equation. And this time it's even less demanding arithmetic. We just factor C out of the sum. What is left is equal to 0 by the assumption that this is a solution. And we have a product of something and 0, and it is always 0. So that new collection is, no prime here, that new collection is also a solution. And that is true for any homogeneous linear system, that the set of solutions is, scientifically speaking, closed under the operation of summing and the operation of scaling. So this is a multiplication by a number or scaling of a vector. So scaling a solution will give us a solution again. In particular, if we scale any solution with coefficient 0, we'll have the vector which is all zeros, which is a solution anyway. Now let's look at the situation where we have something on the right in a linear system, in homogeneous case. The same generic template, we have n unknowns, m equations on them. What we can, so it is no longer true that sums of solutions will be solutions, but there's still something we can say about solutions of the general case. In a general case, again, assume that we have two vectors solving the system. What we can prove is that the difference of them, which will be the vector with coordinates being differences of coordinates. So the first is not prime, second is prime. That will be the first solution vector minus the second solution vector. Is a solution of not this system, but its homogeneous version. So that will be the homogeneous corresponding to the left-hand side. Meaning that when we change the right-hand side to 0, then this new vector of differences will be solving all the equations in the system. So let's again check for one of them. Imagine one of them, say the first, but I will be just skipping the coefficient, the first label telling which equation I'm in. And then I have to multiply my a coefficients with what is going to be the coordinates of the solution, these differences. And again, distributing and rearranging, I will have this time the difference of the same equation with different values of the unknowns corresponding to solutions. Since they are solutions of an unhomogeneous system, they are equal to the same number. I'll call it B. Again, not specifying which equation I'm at. So these numbers, these right-hand sides will be different for different equations, but they will be the same for both of these sums. So I will have the difference of a number and the number again, which is always 0, proving that this difference of vectors is a solution of the homogeneous system. So what we proved in other way is that if we fix one solution of our inhomogeneous system, then all other solutions will be possible to write as this fixed one plus solutions of homogeneous version of the system we have. Geometrically, it will be sort of describing our solution set as a linear object. We have a point on this set, and then we have a solution set of homogeneous system, which is a sort of certain linear object, a line, a point, a line, or a plane, or a hyperdimensional object shifted by this seed point. So that is a convenient, sometimes a very convenient way of writing solutions of homogeneous systems. Examples will appear in the next video. See you then.